Hello everyone. So today we will go through the two-way slab supported on four sides tutorial. In this tutorial we have to solve we will solve and find the design bending moment for the shown slab, which is 4 bay in horizontal direction, 3 bays in vertical direction. The given information about the two-way slabs are as mentioned here. So the slab is supported on beams cast monolithically with the slab. The width of the beam or the stem width of the beam is 300 millimeter. The dead load on this slab is 3.8 kBA or kilonewton per square meter. The live load on this slab is 3.5 kBA. The requirement of this example is to find the design bending moments on the slab using section 6.10.3 of the Australian Standard AS 3600. Also determine the loads that go to the supporting beam on axis XX and the effective flange width of each of its span, and also need to find B effective or the flange width for these three spans, 1, 2, 3. Okay, this example is for two-way slab on four sides. So before we go through this example, I will just briefly explain some of the concepts we need to know for this slab. So let's assume we have a continuous slab consists of two bays like that. We have two directions. This direction is the short direction, L short equal to 5 meter, and we have on the other side or the other direction L long 6 meter. Okay, these two bays or these two slabs are supported by beams on all sides, so on the four sides of each slab. So this is our slab, and you have some columns here. And we need to find the bending moment, positive and negative bending moment on this continuous slab. Okay, so these moments, the design bending moment, will be calculated using section 6.10.3 of the Australian Standard. AS 300, 600, and I will share to you this section on the standard. This section here, the simplified method for reinforced two-way slab supported on four sides. As you can see, the design bending moments are calculating the positive bending moments are calculated using this formula mx asterisk my asterisk beta x fd l x squared and beta y fd l x squared. Okay, so if we go back to our note, so the bending moment, we have two bending moment, mx asterisk, which is the moment in the short direction, and we are looking now for the positive bending moment. So mx in the short direction equal to beta x fd lx squared, and my asterisk, which is in the long direction, equal to beta y fd lx squared. Okay, so we have L short, this is L short, and this is L long. So the moment in the positive moment in L short is calculated using the factor beta x. and the bending moment in the long direction or parallel to y will be calculating using the factor beta y. Okay, these two factors, beta x and beta y, are calculating from table 6.10.3.2a from the Australian standard according to the value or the percentage Ly over Lx, where Ly is a long span, Lx is a short span. So all the time, this percentage should be more than 1. So if we go to have a look on the standard, so this is the table we are looking at here. So using the value of Ly over Lx, which is more than 1, so we can find beta x from these values and beta y from this column here. So another parameter or another information we need is the edge condition for the slab, which we have 9 given or 9 common edge condition, 4 edge continuous, 1 short edge discontinuous, and so on. So we have two things to need to know before coming to find beta x, and beta y. The first is Ly over Lx, and the second is the edge condition of our slab. Okay, so we will go through this in few minutes. So now before we go, we have another parameter we need to know, which is FD. FD is the design distributed load, or W asterisk on the slab. Lx is the short span. Okay, so to know the moment mx asterisk and my asterisk, we need beta x, beta y, and fd and lx. So then, after how this moment works, or how this moment calculated, this moment calculated on based on 1 meter strip width of the slab in short direction. So this yellow one, and the moment in this direction would be using the factor beta x, and on the other direction y, we will have also another 1 meter strip in y direction. Okay, so the moments are based on that. So we have 1 strip in horizontal or short direction, 1 strip in the vertical direction. Each strip is 1 meter side, 1 meter width. Then this for the positive moment. For the negative moment, for the negative moments, if we go to the standard again, so the standard gave us the negative moment here in point B is 1.33 times the midspan values in the direction considered. This is the negative bending moment at continuous edge, and the negative design bending moment on or at a discontinuous edge is zero point 0.5 times the midspan values. Okay, so we have two values of the bending moment, negative bending moment, 1.33 m positive at the continuous edge, and zero point 0.5 m asterisk positive at the discontinuous edge. Okay, what this means? This means that if you have, this is our bending moment strip, or the strip of our bending moment in short direction, for example. So if we have M asterisk here, M asterisk here, so the bending moment here on this one will be 1.33 M asterisk, 1.33 M asterisk. This is a continuous edge. And here, zero point 0.5 M asterisk and 0.5 M asterisk. This is this continuous edge. And the moment shape will be, if you want the bending moment shape. So the moment here, 1.33 M asterisk. Here, M asterisk. And we have here 0.5 M asterisk. Here, 0.5 M asterisk, negative. And here we have negative, positive M asterisk. So the design moment here is M asterisk positive and 1.33 M asterisk. Okay, so this is the moments we want to know for this type of slab. We need positive moment in X and Y direction and negative moment in X and Y direction. So if we look at this example, so I will repeat this part again because I was sharing the other slide. So from the standard, we found that the negative moment should be 1.33 M asterisk positive in the bay we are calculating the moment for at the continuous edge, and zero point 0.5 M asterisk positive at the discontinuous edge. So we have two bending moment. One, if we have continuous edge, 1.33 times M positive, and zero point 0.5 if we have discontinuous edge. How to interpret these two values? This means that if we have our strip, this is our bending strip, and we have calculated the bending moment at midspan as M asterisk positive, and here M asterisk positive. So the moment here at this point, or this is our continuous edge, will be equal to 1.33 M asterisk, 1.33 M asterisk, because this continuous edge. So this continuous edge is the edge support here, or edge end here, which is named discontinuous edge. The moment at this discontinuous edge is zero point 0.5 M asterisk. Okay, so if we want to interpret or draw the bending moment here, so the bending moment here in the positive or the midspan is M positive. On the support is 1.33 M asterisk because this is a continuous edge. And here on the edge, it is 0.5 because this edge is discontinuous edge. Okay, so this is the interpreting of the information we we know from the standard or using the standard. So now if we want to find the bending moment factor, for example, so what we should do, we will have our slab like that. So we have 5 meter, 5 meter, and this one is 6 meter. Okay, so first of all, we need to find what is Lx and what is Ly. Lx is 5 meter, Ly 6 meter. So Ly over Lx equal to 6 over 5 equal to 1.2. So this is our L long and this is our L short. So this is our first step. Then we need to find the value of W, or sorry, Fd times Lx squared. So you can calculate this value based on how much FD. Okay, then we need to find the vector beta x and beta y to find the bending moment. So what we will do is naming our slabs, for example, A and B, and then create a table. So we have only two slabs this time, but we have slab ID, and we have two only slabs. So we have A, B. Then we can add slab edge condition. Okay, then go to the standard and find beta x, beta y. And don't forget this table is for positive bending moment or M positive. Then using the factors beta x times FD L x squared, find M x asterisk, and the factors beta y times FD L x squared to find M asterisk y. So for this problem, our factor is 1.2. And if we look here, the edge condition of this slab is for slab A, we have one edge, two edges, three edge, discontinuous. So this slab is three edge discontinuous, and this edge only continuous. This edge is the long edge, so with one long edge continuous. So if we go to our standard here in table 6.10.3.2, so we know that we are looking at the factor in column 1.2. But what is the edge condition? Our edge condition is number 7. So 3 edge discontinuous with one long edge continuous. So the number of our slab is 7. Okay. So we just put the edge condition in our table as 7. So what you should do if you have many slabs, you like give them ID, then the edge condition based on the table will be number 7. So if we look on the other one as well, the other slab, also 3 edge discontinuous, and this edge is continuous. So it's the same 3 edge discontinuous with long edge, one long edge continuous. Okay, so also this one will be 7. So both of them are same slab edge condition, 7 and 7. So if we go to the table again to find how much is the factor, you will find that the factor for three edges or number 7 is for 1.2.053. So you know is beta x for both of them 1.053 and beta y is 0.043. So we go back. So we have 0.053, 0.053, and 0.043, 0.043. So what you would do next is multiplying this factor times FD Lx squared, and this is same value, so no need to repeat. Here also 0.043 times FD Lx squared, 0.043 times FD Lx squared. Then you find the moments on the positive moment on this two bays. So this is our positive moment. So for the negative moment as well, or negative bending moment, negative, you can also use table. So what you can do is create the table, and we don't need to create many bays because they are same. So A and B in one bay, in one, sorry, cell. So this is slab ID. Then x positive. Then we have two values, 1.33 asterisk, 1.5 asterisk. Then we have my asterisk. Then we have 1.33 asterisk and zero point 0.5 asterisk. Okay, so this is in the long direction, and this one for the short direction. So this is short and this is long. So the value you get here from the first step, multiply by 1.33 and then multiply by 0.55. And the value you get here from the first step, this one here, times 1.33 and times zero point 0.5. Okay, and here is this value. So this is are the bending moments for the slab, the design bending moment, positive and negative bending moment, and using the edge conditions and Ly over Lx and the factor beta x and beta y from table 6.10.3.2a. And this is generally what is how to use the table to find the bending moment. Okay, so what I will do now is start going through the example we have today. So now if we look at our example today, so we have the slab here with again four spans in x on horizontal direction, three span of vertical direction. So I will share my notebook screen again. If we look here. So in this example we have, this is our slab. So this is our slab. We have L long here, sorry, L short, 5 meter each. And here's the long direction, we have 6 meter. And as you know, all the sides of the slab are supported by beams, so all these lines are beams or walls. Let's assume it is beams. Okay, so in this example, we have L long again equal to 6 meter and L short equal to 5 meter. So Ly over Lx equal to 6 over 5 equal to 1.2. And I will give the slabs this IDs A, B, C, D, E, F, G, H, I. So we have 9 slabs. Okay. And given to us in this example that the dead load on a slab or G slab equal to 3.8 kPa and life load on slab Q slab equal to 3.5 kPa. So let's start first with calculating the loads on this slab. So we have FD equal to W asterisk equal to 1.2 G plus 1.5 Q. So we have 1.2 times 3.8 plus 1.5 times 3.5 equal to 9.8 kBA, 9.8 kilonewton per squared meter. So this is the load on our slab FD. So now we can find the value FD times Lx squared directly because all the moment is a factor times FD squared. So can find it now. So we have FD equal to 9.8 times kilonewton per square meter times Lx squared, which is 5 squared meter. So our moment will be 245 kilonewton meter per meter. So this is the value we are looking for, which is 245 kilonewton meter per meter. Okay, you then using the simplified method of the standard in section 6.10.3, the simplified method for reinforced concrete two-way slabs supported on 4 sides. The moment, as you know, are mx asterisk equal to beta x times fd times lx squared and my asterisk equal to beta y times fd lx squared. So this value already known is 245 kilonewton meter per meter, kilonewton meter per meter. So what I will do now is just go to the standard table 6.10.3.2a to find the values of beta x and beta y for the slabs A to H. Okay, so as you know, to know the slabs, to know the factors beta x and beta y, we need to find the edge condition for the slabs. So before we proceed, also, just to remind you that this is our short direction. So beta x will be in this direction and beta y in this direction. So this is our long direction and this is our short direction. So if we look at plate A or slab A, so this is condition 6. So just show you the standard table again. So if we look at the table here, so we have 6 is 2 adjacent edges discontinuous. So here we have discontinuous edge and discontinuous edge to this 2 discontinuous edge, 2 adjacent discontinuous edge. So this number 6. Also this one, B is number 6 because it is 2 discontinuous edges. Number C also 2 discontinuous edge. Okay, also here number I is 2 discontinuous edge, so number 6. So actually 6 is if the slab is on a corner, so it's considered as two discontinuous edges. If we look at D, so D has 4 edges continuous. So if we go to the table again, so we have 4 edge continuous is number 1 or condition 1 because this edge continuous, all the 4 edge are continuous, so this is number 1. E is, sorry, so again here number D is continuous from 4 sides, so it is number 1. E is number 2, which is one short edge discontinuous. So for the long edge, both of them are continuous. Only one short edge is discontinuous. So this is number 2. Okay, if you look here, so this also same, G and H, one short edge discontinuous. So this 2 slabs are number 2. Okay, the last one is F. F is number 8 because it has 3 discontinuous edge, discontinuous edge, discontinuous edge, discontinuous edge. Okay, and only this one is continuous. This one is one short edge continuous. So this is number 8. So this is the this is the edge condition for all our slabs. We have, like, if we define them, so we have A, B, and I, and C. All of them are number 6. So we have 4 slabs number 6, and we have plate E, G, and H are number 2. 3 slabs are number 2. And we have one slab number 8. And we have one slab number 1. So this is the definition of, or sorry, this is the edge condition of the slabs we have. Okay, so now we can create a table with factors and so on to make it easier for us. So for the positive moment, so our table, we have this table. We have a slab ID. We have slab end conditions or edge conditions. And we have beta X and beta Y from the tables. Then we have mx star and my star. Okay, so we have four types of slabs. We have slab number 6, edge condition number 6, edge condition number 1. Sorry, maybe make order in order. So we have 1, 2, 6, and 8. We have one slab with slab edge 1, which is D. We have four slabs with, sorry, three slabs with 2, which are E and G and H. We have four slab with 6 in the condition, which is A, B, C, and I. We have one slab with 8, which is F. So you can go back to the diagram here. So we have A, B, C, I, 6, D, 1, E, G, H, 2, F, 8. Okay, then what we have to do is just go to the table, this table here, just to remind you. So for 1 and 1.2, get this value 0.032. For 2, 0.036, and beta y is 0.028. And for number 6, we have 0.46. For number 8, not 0.064. So I will fill the table now with those values. So we have here for case number 1, we have beta x 0.032 and beta y is 0.024. And number 2, we have beta y 0.028 and beta x 0.036. Number 6, we have 0.046 and beta y 0.035. And we have here number 8, which is the largest value, 0.043, and we have beta x as 0.064. So here, this one, m asterisk x equal to beta x times 245, and here we have m asterisk y equal to beta y times 245, where 245 is fd times lx squared. So the values will be, for number 1, we have 7.84 and 5.88. For number 2, we have 8.82, and for my, it is 6.86. For number 6, we have point, sorry, 11.127, and for my, it is 8.58. For number 8, we have 15.68, and we have for my is 10.54. So this is, or this, those are the positive bending moments for the slabs or for the base we have. And then we will need to create a similar table or a table for the negative bending moment using the positive bending moment. Just a reminder that the negative bending moment, we have two values, 1.33 m asterisk positive and 0.5 m asterisk positive. So this is at continuous edge and this is discontinuous edge. So if we create another table, so we will have different table. So again, we have slab ID, and we have four slabs, four type of slabs. And then we have edge condition. So we have similar to the previous one here, we have D, 1, 2, 6, 8. So this one is F. 2, we have E and G and H. And for 6, we have A, B, C, and I. Then we have M asterisk X. So this one I will make it with a different color. M asterisk X. And we have 0.5 M asterisk X and 1.33 M asterisk X. So these are the values we need for this slabs. And then we will have M asterisk Y, 0.5 M asterisk Y, and 1.33 M asterisk Y. So we have just three values here. Okay, so this is for Y direction or long direction. And this is our short direction. So what I will do, just get mx asterisk and my asterisk from the previous step and put them here. So we have here the value on x asterisk are, for number 1 we have 7.84 and we have 8.82 and we have 11.27 and 15.68. And for the my values, we have 5.88, and number 2 we have 6.86. Number 6 we have 8.58, and number 8 we have 0.54. Then what you will do, just multiply zero point 0.5 and 1.3 times this for values. So the values are, we have 3.92 and 10.43. And here we have 4.41 and 11.73. Here we have 11.27 times 0.5, 5.63 and 14.98. And finally, we have this value is 7.84 and 20.85. So the maximum moment, as you can see, comes all from F. So we have these values here, this value here, and the positive moment is here. Okay, because it has a maximum factor. That's why it has a maximum values of the moment. So here we have, and because it is on the edge, like symbol slab on the edge. So if we look here, so 5.88 times zero point 0.5, just give us 2.94 and 7.82. 6.86 give us 3.43 and 9.12. 8.58 give us a value of 4.92 and 11.41. 10.54 give us a value of 5.27 and 40. So also here, the maximum moments are this value here, this value here, and this value here. So these are the positive and negative bending moments for the slab we have today. So we can just maybe if you want to can put this on the slab slab itself, like draw a diagram for the slab to show the moments on it. So I will draw the slab. So this is our slab. We have here 5 meter, 5 meter, 5 meter. And here 6 meter, 6 meter, 6 meter. So I will put the moment I have got here. So let's put the moment in the short direction first. So this is again our short direction, beta x in red. So we have here 5.63 and 11.27 and 14.98 and here 11.73, here 8.82 and 11.71. So this like we have this our strip here and I put the moment on this strip. So each direction has this 3. So this is for the x for the beta x direction. Then we have here 14.89 98, sorry, 11.27 and 5.63. 5.63 the negative moment on the edge, 11.27, 14.98, 7.84, 10.43. Okay, so I just missed one number, so I will just do it now. So we have 7.84 times 1.33 equal to 10.43. So here also 10.43, then 11.73, 8.82, and 4.41. Here the negative moment is 5.63. The positive moment is 11.27. Negative moment. So this is negative moment, positive moment, negative moment. Negative, positive, negative, negative, positive, negative, and so on. Okay. So here is negative moment is negative 11.73, positive 8.82, and 4.41. Here the maximum value is 7.84, 15.68, and 7.84. So this all the direction in beta x. And now let's draw the other direction, beta y. So we have beta y in this direction, or the long direction. So we can draw it in other order to percent. So we have similar to the other one, we have our strip like that here. So I will put the moment on this line. So here we have 5.27 and 10.54 and 14.0, and here 9.12, 6.86, 9.12, 9.12, 6.86, and 9.12. Okay, here 11.1441, 8.58, and 4.29. Here 4.29, 8.58, 11.41, 7.82, 5.88, 7.82, 5.88. Sorry. This value is 6.86 and 3.43, 9.12. Here 4.29, 5.8.58, 11.41, 11.41, 8.58, and 4.29. So these are the bending moment in X and Y direction. And if we want to point out what is the maximum value, so the maximum value is this one, positive moment, and this one is negative moment for this direction. Sorry, the edge direction of discontinuous edge, and we have this value if we excluded this value. So this value is already the maximum anyway. If we consider the second maximum value to use for the whole slab, so this is the second maximum value, positive, and this is second maximum value negative, and this is the maximum edge. Okay, so this in the yellow in short direction. If we use green for long direction, so we have also here, this is the absolute maximum, sorry, this is the maximum because it is on the edge. The second maximum will be also this value here and this value here. So this is for long direction. So to summarize the maximum values of the moment or the maximum design moment for this slab, we have the maximum design moments in X direction or L short direction. We have M maximum negative and M asterisk positive and negative. We have 14.9 or 0.89 kilonewton meter per meter, and we have 11.27 kilonewton meter per meter, and only 15.7 kilonewton meter per meter, or 15.68 in one slab. So these are our maximum values for X direction or for horizontal for short direction. For long direction or Y direction, L long, we have also M asterisk negative and M asterisk positive. We have 11.6 and this value here. 11.41 kilonewton meter per meter. And we have a value of 14 kilonewton meter per meter only at one slab. And we have the other value is M positive equal to the positive moment, as you can see, is 8.56, 8.58, sorry, kilonewton meter per meter, and 10 point something, 0.54, 0.54 kilonewton meter per meter at only one slab. So the values, the maximum values in this case are for Y direction. We have this value here, 11.41 and 8.58. So this is the design moment requirement for this slab. And then the second requirement was to find the loads on beam XX. So now if we jump to the second requirement, which is loads on beam XX. So if we draw the slab again, so this is our slab. So this is our slab, 5 meter, 5 meter, 5 meter, 6 meter, 6 meter, 6 meter, 6 meter. This is our dimension, and this is our dimensions. So this is the requirement is to find the load on the beam on axis XX. So this is our beam we are looking at. This beam will carry part of the slab. This part of the slab is based on the condition here. So if we have slab, we have L short and L long. So we have beams in short direction and other beams in long direction. So the slab will be distributed to the beams using the concept that this angle will be cracked at 45 degree and 45 degree, and here also we will have same concept here. This angle will be cracked at 45 degree, 45 degree. Here also as well we have same concept, 45 and 45 degree, and then these two cracks uh, will intersect here. So the cracking of this slab will be like that, 45 degree, 45 degree. Okay, so this part of slab here, this green part and this green part will be transferred to the beams in short direction. So this beam here will take this triangle from the slab, and this beam here will take same triangle from slab. So the angle is 45, 45, 45. So if this L short, the height of this triangle is L short over 2. L short over 2. So if this L short, so this is L short over 2, L short over 2. So this is the height of this triangle, L short over 2, because this is L short. Okay, and similarly here, L short over 2, because this is half and this is, so if this L short over 2, so this L short over 2 to make this angle 45 degree. And what will happen to the trapezoidal? The trapezoidal will be transferred to the long beams. So these two trapezoidals will be transferred to the long beams. So the beam in the long direction, really long, will carry this trapezoidal. Also, this is 45 degree, 45 degree. Okay, the height of this is L short over 2. Okay, so this is our trapezoidal here, and this is our triangle here. The load on this triangle is FD in kPa. FD in kPa. Because this is a slab load. Okay, so this is how to distribute the loads on two-way slab. Sorry, the load from two-way slab to the supporting beam. So if we look here, as you can see, this is our beam. So this beam will carry part from slab because this is a short span, so it will carry triangle and right, so it will carry this XX beam. It will carry part from slab like that. 45, 44, 45 and 45 degree, and here will be like that. So this beam will carry from slab this triangle here. The height of this triangle is L short over 2, which is equal to 2.5 meter, because this slab is 5 meter. And similarly from all the other slab, because this beam is on the short side. And the long direction will take the trapezoidal. So our beam, XX beam, will carry one triangle in the first bay and two triangles in the third and second and third bay. So we can interpret that too, that if this our beam loads on beam X, X. Okay, so we will have three bays, each bay 5 meter, 5 meter, 5 meter. Then this bay carry triangle. This bay carry two triangles. This bay carry two triangles. The load in all of them FD. The height of all of them is L short over 2 equal to 2.5 meter. So all of them 2.5 meter high, and the load is FD. Okay. Then if we want to clean the load, or make it more clearer, so we can convert the two triangle to one triangle. The maximum value here, we will find it as W1 now, 2.5 meter, and the load inside is FT. But this load in kilonewton per meter. Then the other two will be bigger triangle. The height of this triangle will be the addition or the summation of 2.5 plus 2.5 to become 5 meter. And again, FD, the value here of the load W2 in kilonewton per meter. And similarly, we have W2 in kilonewton per meter. Okay, so this is the load on the beam we are looking for. This is our requirement for the beam. So how can we complete this requirement? We need to find how much is W1 and W2. So if I ask you how to find W1 and W2, the idea is W1 will be equal to FD times the height of the triangle. So it will be FD for all of them was 9.8 kBA. So it will be 9.8 kBA times 2.5 meter give us a value of 24.5 kilonewton per meter. For W2, we have also FD times 5 meter, the height of the second triangle here, 5 meter. So we have 9.8 kBA times 5 meter equal to 49 kilonewton per meter. So this means that the value here is 24.5 kilonewton per meter. The value here is 49 kilonewton per meter. The value here is 49 kilonewton per meter. So this is the requirement for the beam loading. Okay, the third requirement is how to find the effective width of the beam on XX. The effective width means how much will be taken from the slab with us. So this is B effective. This is called L section because we have slab in one side and this is our other part is B effective here, which is that one here, T section. The stem width here is BW for both of them same. Okay, and here the slab thickness TS and here TS. Okay, where this two can be found? If you cut here, if we cut here in the beam here and here, let's say this section AA and this section BB. In section AA, we will find that we have only slab from one side of the beam. So this is L section at AA because we have only slab on one side. But at section BB here, you have slab from left, slab from right. So at section BB, we have T section. The T section will be something like that. So the beam section, when connected or monolithically bored with the slab, can have L section or T section. The standard give us the value of B effective in clause 8.8.2 of AS 3600 2018 as follows. For T section, B effective equal to BW plus 0.2 A. For L section or the slab from one side, B effective equal to BW plus zero point 0.1 A. So we have zero point 0.2 and zero point 0.1 A for T and L section. Okay. BW is known as the beam stem width, or this one here. This is BW. Okay. So B effective will be W plus part. This part actually on the drawing can be understood as this part plus this part. So in this case, these two together is 0.2 A, and in this case, this is what is meant by 0.1 A. So what is A? A equal to, or the definition of A first is the distance between points of zero moment, zero bending moment. Okay, which indicates that if this our beam, for example, or if this is our slab and this is our supporting beam. So the bending moment on the slab will be something like that. So this is negative, positive, positive. So actually A is the distance from here to here. So this is what is A. So A is the distance between the two zero moments. So the moment here is 0, 0. This is our bending moment diagram. So this is actually A. But A can be calculated using the standard as we don't need to locate the zero moment. A equal to 0.7 L. Okay, so A equal to 0.7 L, which is here. What is L? L here is our span of the beam is 5 meter. So A in our case will be 0.7 times 5,000 millimeter equal to 3,500 millimeter. So now we can find B effective for L section and B effective for T section, which is required in our problem. For L section, we have BW plus zero point 0.1 A, so it is equal to 300 plus zero point 0.1 times 3,500 equal to 650 millimeter. For T section, we will have BW plus zero point 0.2 A equal to 300 plus zero point 0.2 times 3,500 equal to 1,000 millimeter. So to interpret this one, these two values, this means that this is our T section. This is BW equal to 300. So this is our B effective equal to 1,000 millimeter. So this is our cross section is T section. For the other section, which is L section, here we have this is L effective equal to 650 millimeter. And we have BW equal to 300 millimeter. This is our L section. Okay, so this is our second cross section. The L section will be when slab only on one side of the beam. Here, T section when slab on both sides of the beam. Okay, and that's it for the solid slab on four sides, and hopefully you can understand it. If you have any question, please email me. Thank you.